In this video, we'll be dealing with a specific precipitation kind of problem where you're given starting reacting amounts. There's a precipitation reaction, and then it's asking what are the concentration of the ions remaining after the reaction has, or after the equilibrium has been established. So two things are going on. First, we need to treat the the precipitation reaction, which is a one-way arrow. That's a full-on chemical reaction that's not coming back. And then with the product is going to go ahead and do equilibrium because it'll be a insoluble ionic compound, which is going to go ahead and go do equilibrium. So let's start this problem. Um, so we have so we need to calculate. So the first thing that we're going to do is deal with, in this reaction, we have potassium phosphate and calcium sulfide. So the two ions are going to be K plus, or the possibilities for the precipitate, K plus, Ca2 plus, and S2 minus. So it could be K plus and sulfide. So we know that will be soluble. And the other possibility is calcium and phosphate. So that should make a precipitate. That's our reaction. So the first thing we're going to do is deal with the precipitation reaction. Okay. And this is, so you will have starting amounts of both. So this is going to be, recall this is some old stuff. This is going to be a limiting reactant problem. You're gonna have to find the limiting reactant. You're gonna write out the reaction. So use a net ionic equation and set up an earth table. Okay, this is similar to like when we had a buffer. Okay, like if you had components HA and A minus. Okay, and then let's say some strong base was added. Okay, that's going to do a reaction with this. So you do that in an earth table, and then you do an ice table with the things that remain. Okay, it's exactly what's going to happen here. It's no different. The major thing that's different is the stoichiometry. You're going to have some weird charges and subscripts, so the quantities are going to be different, which makes this a little bit more involved. Okay, so for calcium, so here's my reaction. So it's going to be calcium 2 plus and phosphate. Okay, and the way to write this correctly is to go ahead and write the product. The correct ratio of ions is 3 calciums and 2 phosphates, and then you balance it. So I need you need 3 calciums and 2 phosphates here. And now we need to figure out our millimoles starting. So remember, with our earth table, we're going to be working with millimoles here. Moles or millimoles. It just so happens in this problem it's easier to work with millimole. For the calcium ions, we have 85 milliliters. So this is our amount of calcium ions we're going to get from that. So 85 milliliters times 0.250 molar, and I get 21.3 millimole. Okay, so I'm going to enter 21.3 millimole into my table. And then for the phosphate, I have this. Okay, and this dissolves in a 1-to-1 ratio, so I don't need to multiply the molarity by anything. So this is going to be 75.0 times 0.150 molar. So for this, I get 11.3 millimole. Okay, so I'm going to enter that here, 11.3 millimole here. Okay, so now it's a limiting reactant problem. So I wrote out my net ionic and I got my millimoles starting. So I'm going to compare those over here on the side. So I have my actual amounts. I usually like to put the bigger number over the smaller number. In my actual amounts, I have 21.3 calciums and 11.3 phosphates. Okay, and I'm going to compare that to the required amounts by the bounce reaction. So I require a 3-to-2 ratio. So I like to reduce the denominator to 1, so I divide those two numbers just because it's easier for me to analyze. So I get 1.9 over 1, okay, compared to, and I divide this one as well, compared to 1.5 over 1. So the correct way to analyze this is I require 1.5 calciums for every 1 phosphate. What I actually have is 1.9 calciums for every 1 phosphate. So what that means is I have too much of this one because I only need 1.5. What I have is 1.9. So if I have too much of that one, that means the other one runs out. This is the limiting reactant, the phosphate ion. Okay, so I'm going to subtract. So all of this runs out, so I'm going to subtract all of it. So this amount should go to 0. Okay, if you're ever asked to solve this problem, only asks for the ions remaining. So, but if you were asked for the amount of solid formed, this starts off as 0, and then you could calculate that number now. But right now, we need the amount of calcium that reacted. Okay, remember to use this number. Once you determine the limiting reactant, we use this number for the reacted and formed amount. So the amount of reacted reactant of the other reactant and the amount of formed product. So we use this 11.3 and then the mole ratios in the problem. Okay, so I'm going to use this 2 to 3 ratio to get this number, the amount of calcium that reacted. Okay. So I'll do that in, I guess I'll do that in red right here. So this star matches up this work right here. Okay, so I'm going to get, so I have 11.3 millimole of PO4. Okay, and then 3 moles of calcium, or millimoles of calcium, react for every 2 millimoles of phosphate. Okay, so that unit cancels. Okay, and this amount I get is 16.9 something, or it rounds up to 17. So minus 17 millimole here. Okay, so this red work I did corresponds to how I got this number here. Okay, now if I subtract those, I get 4.3 millimole of calcium left over. Okay, and if you were interested in this number, you can do that also right now. This problem doesn't ask for it, but if you wanted it, you could do this number here. Okay, so and I'll do that work right here with this green ink. So 11.3 millimole of PO4. And then 1 millimole of calcium phosphate forms every time 2 phosphates react. My work is getting very crowded here. Okay, so this number would be, if you were interested, 5.7 millimole. But like I said, this problem doesn't ask for that. But if you wanted to know how much solid form, you can figure it out from there. All right, so you would just use the molar mass and whatever. Okay, so now what do we do? So the next thing to do, that's the first thing to do, is you deal with the precipitation reaction, the chemical reaction. Okay, one-way arrow, not coming back. Okay, and now the next thing we do is we run these amounts, this amount and this amount, in the ice table. So this will go ahead. So this solid will go ahead and make do equilibrium with its ions according to its KSP, and that's what it's asking us. Calculate these amounts remaining after equilibrium is established. Okay, that's the next thing. I'm actually going to continue this on the next slide. I'm out of space here. So that's the second thing to do is now the solid that formed will do equilibrium with its ions. Okay, and now what we want to do now is carry over. So we're going to carry over the F line molarities, because we're doing an ice table now, carry over the F line concentrations into the initial amount on the ice table, the initial amount on the ice table. So CaPO42 will dissociate the solid that formed. We had 5.7 millimoles of solid. The solid that formed goes ahead and does some equilibrium according to its KSP. Okay, we, as usual, dash out the solid. And now we have a common ion because there was leftover. So this is the amount right here is from the F line. This is from the F line. Okay, and we've created a common ion from the leftover. Okay, and this amount was 4.3 millimoles. This amount was 4.3 millimole. And now you have a new volume because it's been mixed, so it's going to be additive. Okay, the two volumes are added. It's going to be 75 plus 85 milliliters here. Okay, so that's where that number came from. And this amount was 0. This is also from the F line because that amount was the limiting reactant, so that was 0. This will go up by 2x. This will go up by 3x. So we have 3x. So I went ahead and calculated this number. I got 0.027 molar. Okay, and then this amount is 2x. Okay, so my KSP for this, let me see if I gave that in the problem. I didn't. Okay, the KSP for calcium phosphate is 2 times 10 to the negative 29th. Okay, and so that's so small, I'm gonna assume that x is nothing compared. This number is massive actually compared to what x is gonna be. So I'm gonna use the assumption rule. Okay, I'm gonna set this equal to. I prefer writing these out so I don't mess up on my exponents. Okay, phosphate is gonna be squared. So this is gonna be 0.027 cubed times 2x squared. Okay, so, and this will be, let's do the math out. So square the 2, that'll be 4, and then square the x, so 4x squared. Okay, so solving for x, I have this. So I'm going to have the KSP, which is 2.0 times 10 to the negative 29th, divided by 4 times 0.027 cubed. Okay, and then I'm going to square root both sides like that. Okay, that should be right. Okay, so I'm going to do a parentheses. I'm going to use this fraction form on my calculator. Okay, and try to enter this all in one shot here. Times 0.027 cubed. Okay, and then square root this. So I'll take it to the 1/2 power. Enter. And I get 5.0 times 10 to the negative 13th. Okay, so x equals 5.0 times 10 to the negative 13 moles per liter. Okay, now it said calculate the amount of calcium at equilibrium. So the amount of calcium is going to be 0.027 molar plus 3x. As we see, x is so small that doesn't affect this number. So that's the answer for calcium at equilibrium. Okay, and the amount of phosphate is going to be 2x, which would be 10 times 10 to the negative 13th, or 1 times 10 to the negative 12th molar, okay, or moles per liter. All right, so that's how you do these. Just to recap, we want to notice that there's two starting reactants, so we need to set up the chemical reaction, one-way arrow, and we get our millimoles of both. We got to figure out which one runs out, okay, so that we know which one goes to 0 and which one's left over. Okay, and then these two amounts on the F line, just like on those buffer problems, these get carried over into here and here. That's from the F line. Okay, and then this, what we're trying to do is figure out, what we're trying to figure out is like, now that you have this solid, okay, how many ions is this solid going to go ahead and make based on its KSP? So that's this process right here. Okay, so we set up this from the solid that formed, and this amount is the leftover, okay, from the chemical reaction, these two amounts. Okay, and then we run this through the ice table and solve. Okay, and we get the amounts at equilibrium. So here's the your turn. So I have two that are just like it. Okay, you'll see. So follow the example carefully. Do the stoichiometry. Do the ice table, and you should be able to get these right. It's the end of our video.